Thanks for joining us this afternoon. Welcome from our organisers, IOTA, Southeast Water and RMIT. My name is Anna Minns. I'm the CEO of Boomerang Labs and advisor at Circular Australia. We have some fantastic speakers here today to talk about PYROCO. We have Dr. Aravind Surapineni, who's going to talk about the problem that we're solving. David Bergman to talk about the research and development. Kalpit Shah to talk about the PYROCO technology and why it's the right solution. And Eamon Casey to talk about the business case. Before we begin, I'd like to talk briefly about the circular economy and water and wastewater. Currently, we operate in a linear economy where we have a take, make, waste model of growth. We take resources out of the earth, we turn them into products and then throw them away. We are heading into a resource-constrained future. As we head towards 2050 with 10 billion people in the world, there simply won't be enough resources to sustain consumption without a circular economy approach. The EU has compiled a list of critical raw materials, and they include things like sand, natural rubber, and many that are needed for an energy transition. While we're running out of natural resources, we're creating an unprecedented amount of waste. By 2050, it's predicted that there'll be more plastic than fish in the world's oceans. Global demand for fresh water will exceed viable resources by 40% by 2030 if we continue with business as usual. There needs to be a dramatic change in the way water is used, managed, and shared. And we can address this with a circular economy. And a circular economy, it's not a silver bullet, it's not a simple solution, it's a systems change. It's the decoupling of economic growth and development from the consumption of finite resources. I think that the circular economy is best summarised in 3 points. Firstly, it's designing out waste. The bulk of waste can be avoided at the design stage. Just a couple of examples that I like to share. Barilla Pasta, I'm sure lots of people are familiar with that brand. They now have a line of paper packaging made from the byproduct of pasta production. Adidas shoes now make a shoe with nothing other than polyurethane. It is no glue, it is produced with heat. So therefore it's designed for disassembly. It can be recycled and turned into a new shoe. Secondly, the circular economy keeps products and materials in constant use. There is no waste, it's just a resource for something else. And thirdly, and most importantly, it is regenerating natural systems. Circular economy is about mimicking nature because in nature, there is no waste. Water authorities have an important role as resource stewards, and the circular economy approach can be applied to water by mimicking nature. In nature, every flow that comes out of a system is an input for another system. The PYROCO innovation we will hear about today is a circular approach to wastewater because it keeps products and materials in use and it regenerates our natural systems. Currently, there is underway a transformative change in the water industry. It's becoming an engine for circular economy. Water authorities have been early adopters of circular economy technologies and practices. The way we think about the role of wastewater treatment plants is changing and evolving. They have an opportunity to become powerhouses of reusing and recycling resources. They are design resource factories, energy generators, used water refineries, and biofactories of the future. And that brings us to PYROCO. In partnership with RMIT University, Intelligent Water Networks, and Greater Western Water, Southeast Water is helping to prove PYROCO. PYROCO is an RMIT innovation, and it offers water authorities a carbon-positive approach for managing biosolid waste. RMIT and Southeast Water have been working on this more efficient pyrolysis approach for the last 5 years. Most treatment facilities manage sludge waste through drying, stockpiling, and transporting for land spreading. Contaminants and biosolids like PFAS and microplastics are a problem and reduce the option for conventional land spreading. The benefits of this innovation are many, and I'm just going to name a few. The PYROCO pilot plant produces biochar with no detectable PFAS. There is a reduction in waste volumes, a diversion in waste from landfills, less transport cost and emissions as a result of land spreading. It's unique in that it can accommodate various feedstocks such as organics or outputs from agriculture, making it attractive for regional organic networks. The biochar created has an incredible pore structure and capacity to hold things within that structure. The PYROCO plant is portable because of its modular and small design, and it is scalable. It is an Australian homegrown technology, and it's the first of its kind in Australia. So I'd like to welcome our panel. I'd like to begin with Dr. Aravind Suryapaneni, who's going to talk to us about the problem to solve. As Senior Research and Planning Scientist at South East Water, Aravind drives the recycled water, biosolids, waste management, soils and groundwater programs that will contribute to the understanding and management of product risk. Aravind, can you talk to us about what is the business as usual practice at South East Water to manage biosolids?
Thanks, Anna. Thanks for the great introduction. So I'm sure water industry professionals knows what biosolids are. For an average punter, biosolids are treated sewage sludge produced from a typical sewage treatment process. At Southeast Water, we produce around 2,600 tons of dry biosolids per year. In terms of treatment grade, our biosolids are of highest quality. We manage our biosolids in accordance with the current edition of Victorian EPI biosolids guidelines. We use them beneficially as a fertilizer and as a soil conditioner for the purpose of growing pastures and fodder crops for cattle. And a recycling of biosolids is a sustainable way of returning valuable nutrients to the soil, which were removed during the harvesting of crops in livestock production. Biosolids improves soil structure, improves moisture holding capacity, and also improves soil fertility. In essence, Anna, agricultural route is our plan A option for managing Southeast Water biosolids.
And what is the problem in continuing with this plan A business as usual practice?
Good question, Anna. There is nothing fundamentally wrong in this least cost and most efficient agricultural use of biosolids. And by the way, we mastered this plan A management of biosolids all these years. But there are three areas of concern. Firstly, I joined Southeast Water in 2009 with a background in agriculture and soil science. I asked myself this question: if Southeast Water were my own business, would I put all eggs in one basket and rely 100% on land application of biosolids? The answer is clear no. Although Australia's water industry has established successful forms of biosolids management, it is important to consider how to adopt it to the changing environment. Problems, real and perceived, associated with the land application of biosolids still exist. If this route is closed for some reason or other, there is no plan B option for Southeast Water. So that is number one. Secondly, finding suitable agricultural customers for land application is in the close vicinity of sewage treatment plants, especially in our operational area, is not always an easy undertaking. And thirdly, forever chemicals like PFAS in biosolids could potentially limit land application. Southeast Water is reviewing the implications and benefits of the proposed regulations following the recent release of PFAS National Environment Management Plan version 3 for public consultation. So these are the three concerns.
So what research effort have you undertaken to look for a plan B option for managing biosolids?
Good question, Anna. As a couple of master's projects from RMIT University that I co-supervised in 2017 and 2018 demonstrated the potential for converting biosolids to biochar using a conventional pyrolysis unit available at the time. The biochar in both these studies, even though resulted in increased total heavy metal concentration, exhibited large decreases in bioavailable heavy metal concentrations. The biochar also showed a favorable changes in several chemical and physical characteristics like pH, plant available phosphorus, pH at plant available phosphorus and surface area. This is for agricultural land application compared to their original biosolids. So these two masters projects and a resultant peer-reviewed scientific publication paved the path for a larger body of R&D on biochar in collaboration with RMIT University and Intelligent Water Networks. So in summary, Anna, the need to move forward quickly and deliberately on this Plan B option to convert biosolids to biochar has become more imperative as the regulators begin to give more stringent advice on contaminants like PFAS, as evident in the recently released draft NEMT 3.0. Thanks, Anna.
Thank you very much, Aravind. Next, we're going to hear from David Bergman, the Research and Development Manager at Southeast Water, to talk about the R&D to do with PYROCO. David has worked in R&D roles in chemicals, detergents, food, manufacturing, and now water and wastewater. He is passionate about innovation and delivery of solutions that make a difference. Welcome, David. Can you talk to us about the approach you have taken to solve this problem?
Yeah, thanks, Anna, and welcome everyone this afternoon. Yeah, our approach to solving the problem really has had two aspects to it. Firstly, there's been a partnership aspect to what we've done, and the way we've worked with RMIT has been the major partner in the development process. We've also, for them, they have the science and the scientists and the engineering background that have been able to work with us through the process. They've been able to do that fundamental experiments back in 2015-16 that Aravind just mentioned before, that really opened the science for us and opened our eyes about what was possible. We've partnered through Intelligent Water Networks in Victoria, which has given us access to all the water utilities in Victoria to be able to engage with them around this common problem we all have to solve. And also too, we've partnered with Greater Western Water, who were able to provide sites for the pilot plant access and licensing for us to really be able to demonstrate at that pilot plant scale. And the other aspect to our approach has been what's on screen at the moment is the staged approach to what we've taken to the development. So Aravind's touched on that fundamental master's project back in 2015-16. From there, that really cracked it open for us, and we were able to move in partnership with RMIT around 2017-18 into laboratory scale experiments, benchtop experiments, where under controlled environments where we were really able to understand the conditions and the materials, still at a small scale, analysis of the pore structures and the contaminant levels as well, which gave us the confidence then to move into a semi-pilot scale, which was really had at its heart the core reactor and enough of supporting systems around it to take now into the next scale where we were able to make kilograms of the product as distinct from grams before, and really gain confidence in the core reactor technology. Then where we've been in 2021 was the pilot plant facility that was based out at the Melton plant for Greater Western Water. And it was there where we're able to process through hundreds of kilos of biosolids into biochar at a new scale again, track the emissions, understand the contaminant levels again, and really also at that site through that staged approach really enable us to get more learnings, but engage with more people by coming to the site and looking at what we were doing, explaining it and understanding it better.
Yeah, great. And so what has been the benefit of this approach?
Yeah, really, if I pick up perhaps the partnership aspect to that, by bringing RMIT into it, obviously they have, and you'll hear from Calpit shortly, expertise in the pyrolysis reactor. We're water people. We don't understand that kind of technology. And so we're able to bring in the experts in the field that are able to work on this outside of our business as usual. We can get quite caught up in the day-to-day of what we need to do, whereas RMIT's been able to, within their research environment, work away and obviously engage with us and collaborate with us as we go. The other partnerships, Intelligent Water Networks, that's about, you know, really reaching out into the industry and making sure that we're including everyone in the problem to solve. And what the researchers get out of this as well, RMIT, the benefit for them, this partnership approach, is they get the access to the real industry problem. Their research is grounded on a genuine problem to solve that we have around biosolids. It's not theoretical, it's not made up, it's a genuine problem that's needed to solve for us. And the benefits of that stage approach that we mapped out before is a real opportunity to low investment early on those smaller scales, and we can learn, build the learnings into the next scale and progressively increase our investment and our learnings as we go and build the learnings into the next phase. So really pace our investment, reduce our risk as we go as well, so that we're not jumping to big dollars and big investment that fails. We progressively work our way through, and that gives us the opportunity to engage with the innovation ecosystem as we go as well.
Fantastic. So what else is in the biochar R&D pipeline for Southeast Water and your partners?
Yes, plenty still to do. So we're at that point now where we have an approved business case for the next scale of the pilot plant of the pyrolysis. So that's a demonstration production plant. So we're in the planning and contracting phase of building that will be able to be running hundreds of kilos through that for extended periods of time, where we will be tracking product material quality in, product quality out, emissions, operating conditions through that project. Also, we'll be able to engage with more potential partners, taking the opportunity to engage in commercialisation options and licensing options as well, by being able to demonstrate the technology in that pilot plant. There's still plenty of surrounding research going on in this. Co-pyrolysis with other materials. There's plenty of materials that are within our local region that would go very well with the pyrolysis of biosolids to be able to create new types of materials, new quality of materials. Also to better understanding contaminant destruction through the process, and also then how do we optimize the process to produce new material, new carbon materials, higher value carbon materials that are not just for agriculture, but maybe even in applications beyond agriculture that can have higher value for and help return on the investment there as well.
That's wonderful. Look forward to seeing all that play out.
Thank you, Anna.
I'd now like to welcome Calpit Shah to talk about the technology and why it's the right solution. Calpit is a professor and group leader for waste and resource conversion technologies in the chemical and environmental engineering discipline at RMIT University. He is also a deputy director for the ARC-funded training centre on transforming Australia's biosolids resource. Calpit, what is pyrolysis and how is it different to other thermal processes?
Thanks, Anna, for the question. And thanks, Arvind and David, for really explaining the journey from a Southeast Water side. So in terms of pyrolysis, in terms of thermal processes, there are mainly three thermal processes: pyrolysis, gasification, and combustion. Now, combustion occurs at a very high temperature, greater than 900 or probably even over 1000 degrees. And that occurs in the presence of excess oxygen that you provide via air. So it's essentially you burning something. That's called combustion. Gasification occurs at medium to high temperature, which is in the range of 700 to 900 degrees centigrade. and oxygen environment is partial present there. So you don't provide a lot of oxygen, but you provide oxygen just sufficient enough to produce syngas. While pyrolysis occurs at low to medium temperature and in the absence of oxygen. So you're not providing any oxygen, any air to the process. Now, lower temperature and absence of oxygen offers significant advantages in pyrolysis compared to gasification and incineration. For example, when you have lower temperature, you will have lower NOx and SOx emissions as well as heavy metal emissions. So your back-end system, which requires to capture all these toxic gases, would be much more simpler and cost-effective. Second, you would have a higher carbon sequestration when you don't have oxygen present, plus your temperature is very low. And third is you will produce superior quality biochar with the lower temperature and absence of oxygen, because you can retain a lot of oxygen containing functional groups. You can also achieve higher carbon stability and a higher surface area as well.
And how is the RMIT developed PYROCO technology different to conventional pyrolysis?
So RMIT technology is first of its kind fluidized bed heat exchanger device. So as its name suggests, what we've tried to really achieve is via fluidized bed and heat exchanger devices integrated in a one common platform, we have significantly improved heat and mass transfer. So that heat and mass transfer really helps you reducing the overall volume of the reactor, and hence you will have a higher throughput. The reactor is also made of simply tubes and pipes. It does not have any moving part. So it has a very high plant availability with much lower maintenance or a shutdown. And it's very easy to fabricate, operate, and maintain as well. And also while designing PYROCO, we have ensured that PYROCO can be flexible to operate with a varied feedstock quality. For example, if you have a lower calorific value or a higher moisture or a lower solids content feedstock, you can still pyrolyze that with PYROCO and still produce some waste heat and high quality biochar.
Well, in regards to the biochar, what are the key differences in the properties of biochar produced by PYROCO compared to biochar from other thermal processes?
So PYROCO, as I said, because in pyrolysis, we don't have any oxygen present and the temperature we have kept as low as possible, PYROCO will have a very high amount of fixed carbon compared to any other thermal processes. It will also have a higher oxygen containing functional groups, higher cation exchange capacity, and also moisture holding capacity. PYROCO biochar will also have a reasonably higher pH and a surface area. And the more important part is the carbon, the biochar that is produced from PYROCO. The carbon in that biochar will be highly stable for at least 100 years, if not 1,000 years. And the other part is PYROCO is kind of a quite flexible technology. So it has an ability to functionalize biochar according to the market needs and application.
Wonderful. Thank you so much. I'm sure there'll be lots of questions for you at the end. And finally, I'd like to welcome Eamon Casey, the Technical Director at IOTA, to talk about the business case. Eamon leads IOTA's Design Solutions team, continuing to lead advances in pressure sewer. He has 29 years of experience in the water and wastewater sector. Welcome, Eamon.
Thank you, Anna.
Eamon, please tell us, what are the key considerations for a business case?
Well, I suppose, firstly, I'd say Southeast Water has now approved a $5.64 million business case for the development of a fully automated pyrolysis PYROCO plant based on a capacity of 3,000 dewatered tons per year. And really that came from the confidence built on the pilot plant's success. The three key pillars, I suppose, of the business case relate to the cost, our net zero targets, and a risk and opportunity consideration.
Can you provide details of the cost considerations?
Yes, yeah, absolutely. So we undertook a fairly detailed comparison of our business as usual costs and the costs of producing biochar for all of our biosolid stock, which will be quickly growing to about 6,000 tons per year, dewatered biosolids at about 50% dry solids. Currently, our unit cost per ton of biosolids, dewatered biosolids, is around $200, $204 to be exact from calculations. That's increased quite significantly over the last year because of our application rates reduction as a result of PFAS controlling application rates, PFAS within our biosolids. And of course, those PFAS recent guidelines have further reduced that potential application rate. So that's a $1.2 million cost for South East Water per annum at the moment. The detailed business case we undertook for the biochar option resulted in a business case or an equivalent unit cost of $136 per ton of biosolids. So we're looking at an operational cost reduction over a 20-year life of the plant.
Fantastic. And what is the impact on net zero ambition?
So South East Water, like many utilities, has a net zero target for 2030 and a 45% reduction in emissions by 2025. From a biosolids perspective, the scope 1 emissions mostly related to ammonia and nitric oxides is quite difficult shift. From a calculation perspective for the biochar project, we're looking at the current emissions from business as usual, so the emissions associated with stockpiling and land application. And we will be removing those stockpiles by converting to biochar, so removing those emissions. And we're also looking at the sequestration, the long-term sequestration of carbon within the biochar, which Calpit alluded at. We calculate our current emissions through the NGERS methodology, so the National Greenhouse Energy Reporting methodology. Our land application, our stockpiling and land application result in the region of 1,300 tons of carbon equivalent emissions per year based on those calculations. If we were to convert the full 6,000 tons of dewatered biosolids to biochar, we're looking at a carbon sequestration, and that's a net carbon sequestration taking into consideration the operation emissions associated with the biochar plant of around 1,000 tons CO2 equivalent. So when we take both sides of that equation, we're looking at about 2,300 tons of carbon dioxide equivalent reduction in our current emissions, which for our scope 1 emissions in South East Water is about 19%, so quite significant.
Absolutely. And you mentioned risk and opportunity. Can you elaborate on that?
Yeah, sure. So from a risk perspective, the risk is really to do with the viability of current practices around stockpiling and land application. The recent PFAS NEM 3 guidelines, which I think were mentioned previously by Arvind, which were published only in recent weeks for discussion, the impact of those limits will mean a significant reduction in our application rates, which really put into question the feasibility of those applications. So that's a significant risk to current practice, and really we're de-risking that through conversion to biochar. I suppose the other risk is our difficulty in shifting Scope 1 emissions. So the ability to avoid ammonia and nitrous oxide emissions through stockpiling and land applications is challenging. So again, we're de-risking that by removing biosolids from the equation. And then on the opportunity side, with the technology that's being introduced through PYROCO, we have the opportunity to pyrolyze other organic wastes within our catchment, whether they be food and garden waste from local councils or from commercial industry in the area. But the opportunity to convert other organic wastes, some of which are going to landfill at the moment, through a process which sequesters that carbon, generates energy, and generates an end use product that we can sell to the market is hugely valuable.
For you, what have been the key takeaways from the business case process?
I suppose the real key takeaway is that we can achieve some really good environmental outcomes whilst also reducing our overall cost. And really that's the key takeaway for me, is that this will reduce our costs, reduce our risks, and improve our environmental outcomes. So it's a very compelling business case from that perspective.
Thank you very much. And thank you to all our speakers today. And that leaves us quite a bit of time for questions, and we have quite a few coming in already. So we've got our first question for Aravind. Aravind, what are the key differences in the properties of biochar produced from biosolids compared to biochar produced from other feedstocks?
Oh, great question. So make it a bit more simpler. So the biochar, the heavy metal concentrations will be increased. I'm talking about the biochar coming from the biosolids as a feedstocks, and the organic carbon in the biosolids biochar will be around 22%. Not great compared to the biomass as biochar. So our biosolids biochar will have fundamentally two drawbacks, if you like. Think about it. Heavy metal concentrations are higher, and the organic carbon is slightly lower. The one that I think David mentioned about co-pyrolysis, and Emil mentioned about bringing organic feedstocks to co-pyrolysis as well. So both this co-pyrolysis, bringing in other organic biomasses which are low in heavy metals and high in organic carbon will enable us to make our biosolids, a better product quality, if you like. So there are the differences between the biosolids biochar and the biomass derived biochar.
Okay, thank you. David, some questions for you. What has been the key to the partnership success? And if you could go back and start again, would there be anything that you would do differently? And then finally, and I'm happy to ask this one again, tell us more about the high value carbon nanomaterials.
Yeah, thanks, Anna. So, sorry, hit me with that question again. Sorry.
Yeah, sure. Why don't I do one at a time?
Yeah.
What has been the key to the partnership success?
Thank you. Yeah, I think it's been the fundamental research that RMIT's been able to do, so that the genuine science, but then also having the frank and difficult exchanges you need to have to sometimes as you are developing science and technology, and having spent the time actually to develop the relationship so it will survive those conversations. Aravind, Kalpit, Aim and myself, we're still all talking and talk regularly because we've had some difficult conversations along the way. So I think that's part of really the open, honest conversations.
And if you could go back and start again, would there be anything that you would do differently?
Yeah, I think one of the things would be around perhaps the way we manage the project. We'd perhaps apply some more project management resources into it. We're a bunch of scientists and engineers that just love the science and are working on in that way. Some higher level discipline project management, perhaps to this point in time, and we're bringing that in now for the next stages. So I suppose we've made it here and in the way that we have too. I think also possibly if we'd had the chance to go again, we would have found more money and resources to run the pilot plant for a bit longer. But limited budgets and limited time and access and availability, we would have done that for a bit longer perhaps if we could have. But our plans for the demonstration production plant, we've built that in, and our plans will be to run that for between 6 and 12 months and get the scale of learnings that we really need.
And there's one more question here for you, which is tell us more about the high value carbon nanomaterials.
Yeah, thank you. And I'll start that question and maybe I'll hand that off to Kalpit to finish that. So through part of the research program that sat alongside the semi-pilot and the pilot plant scale has been some series of experiments run by Kalpit and his team where they've been able to run the pyrolysis in an alternative mode that really favours carbon vapor deposition, and Kalpit will correct my terms, on a biochar structure there already. That's initial results are showing carbon nanotubes, graphene type materials can be deposited on the surface of that, as well as the generation of a hydrogen rich gas. So for us, as a possible alternative mode, still on basically the same set of kit, is really exciting about the potential for that, because once we're talking those type of materials, we're talking possibly a whole new market of application, batteries, electronics, those kind of things that use those kind of high value carbon materials. Kalpit, did you want to add anything to that?
I think you've answered well, David. I'll just add that the reason for us doing the chemical vapor deposition on the biochar surface via biogas was that biochar produced from biosolids had higher heavy metal contents, and no one likes that heavy metals, but chemical vapor deposition likes heavy metals because those heavy metals are finely dispersed in biochar matrix that makes them suitable as a catalyst for chemical vapor deposition type reaction. Now imagine you kind of covering the whole biochar with the high value carbon nanomaterials, which you can directly use as a carbon nanomaterial coated biochar, or you can just simply exfoliate the carbon nanomaterials and sell it in the market. So that's where the values of biochar is further enhanced.
I have a question here that I'll leave open to answer, which is, are you familiar with the PYREG technology? If so, how does your pyrolysis process differ from that established technology?
I'll answer that, Anna. So PYREG, yes, we have, during the first year of the project, we reviewed a number of technologies, and PYREG was one of the technologies we have reviewed, and we have also visited their plant that they put in collaboration with Bio4CTech in California. So the PYREG reactor is an auger type technology, while PYROCO is a fluidized bed. So in terms of the advantage that PYROCO offers is that PYROCO has higher heat and mass transfer coefficient. It can achieve uniform temperature throughout the reactor, and hence the product quality would be much more superior. It's much easier to scale up. And overall higher process efficiencies. So I'm not undermining the efforts put by PYREG or any other technologies, but fluidized bed on its own tells you, gives you all the information. So if you read the literature, enough literature, there is always mention of fluidized bed, which can offer higher heat and mass transfer, as well as higher uniform temperature distribution throughout the reactor. So that can have higher process efficiency and a higher product quality.
Great. We have quite a lot of questions coming through, so we will get to as many as we possibly can, and then we'll connect with those who've asked questions that we haven't had time to get to. But I'll just keep asking these questions and then leave it to the panelists to decide who's best to answer these questions. Were the gas outputs analysed for precursor compounds? Calvert, did you want to? Or?
Calvert, do you want that? I can start on that one. So what we're able to demonstrate at the pilot plant scale is that PFAS, those materials and other contaminants, organic contaminants, were removed from the biochar that were present in the biosolids. A more comprehensive study of the PFAS precursor or PFAS breakdown products that will be part of the demonstration production plant scale that we'll be doing next in that, because that's quite a difficult study and a comprehensive study. Calvert, do you want to add to that?
Yeah, David, I think what we did is we did PFAS, microplastics, pharmaceuticals, pesticides, whatever you find in biosolids. We tried to really do a comprehensive characterization. We got some answers. Majority of the analysis suggested us that biochar is free of those contaminants. However, we still need to do a proper closed mass balance to see where exactly those products are going and are they sufficiently destroyed within the process and being captured safely.
Great. How many hours runtime have the team been able to experience under demand load? The presenter, I'm not sure who that was, had mentioned hundreds of kilograms. How many hours does that equate to?
I'll start that one and I'll hand off to Calvert again. So the July 2021, the pilot plant was run out at Melton across broadly a period of about 30 days that involved all sorts of testing and commissioning in that point in time. So that was run, I think, a total number of hours, 118, 120, around about there, in actual pyrolysis mode. We were feeding in, I think, at hit rates of 30 kilos an hour of the biosolids, but this is where I'll let Calvert pick it up from here for some of those numbers.
I think you rightly pointed out, David. So including commissioning, we probably ran the kit for about 200 to 220 hours. We particularly ran about 14 to 15 days, 10 hours to 12 hours a day, actual pyrolysis runs, while the rest of the time we were just heating and then cooling the system because we were not operating at the night for the whole run. But demonstration plant, we would like to run on a continual basis, 24/7, and as David mentioned, over at least 6 to 12 months to get the full operational data.
I have a question for Eamon. Eamon, have you calculated a reduction in transport costs, transport emissions from biochar versus biosolids?
We calculated our emissions associated with transport, which was relatively small as it happens, probably about 5% of our overall emissions associated with the business as usual biosolids, stockpiling and land spread. So relatively small. We're looking at a volume reduction of 2/3 with biochar. Actually, we're looking at because of the moisture content, we're looking at a volume reduction about 80% with the biochar. So what was a relatively small emissions percentage will reduce by 4/5, depending, of course, on where we deploy the biochar.
Thank you. And what are the power requirements for the PYROCO solution in terms of kilos processed?
You're on mute, Kalpit.
Sorry, yeah, just yeah. So in terms of the electricity requirements, it would be 6 ton a day pilot plant would be roughly you're looking at around 200 kilowatt auxiliary power requirement. In terms of its thermal energy requirement, pyrolysis plant, the PYROCO will be operating in an energy neutral mode, particularly thermal energy wise. So there is a lot of energy required for drying and also running pyrolysis. We will be providing that energy from combustion of oil and gas vapors, because oil and gas vapors you need to combust to ensure that you destroy all the PFAS and other contaminants present in biosolids. So as I said, in terms of electricity, it's about 200 to 250 kilowatts for a 6 ton a day plant. But in terms of thermal energy, it doesn't require any energy there.
Great.
It will in fact produce surplus waste heat.
And this may be another question for Eamon. Is there a minimum plant size for biochar biosolids production to be viable?
In terms of a minimum size, our approach has been to pick an optimal size for our needs with consideration for a modular solution. Southeast Water has 8 wastewater treatment plants, of which a number are quite small regional lagoon-based plants, and of course with an eye on regional Victoria. So we would envisage that a modular plant in around the scale we're talking about, 6 ton a day, would be the optimal solution for smaller decentralized plants. Obviously the bigger the scale, the more efficient the process. So I would say the biggest modular plant is the right solution for smaller locations.
Can I just follow that up with another question, which is what is the model of commercialization for PYROCO?
So we will build this first plant over the next 18 to 24 months, and that will really prove out the capital and operating costs and the biochar quality and emissions. So when as part of that process, it's our intent to provide an opportunity for others to share in that process. Now we're looking at the moment at what the best model for that is, but certainly we fully intend to make it commercially available within the model that suits the market in the next 18 months.
Okay. Again to the panel. What is the minimum solids content of sludge feed to the pyrolysis degree of dewatering? And what amount of energy is needed per tonne for the process, and how will this energy be sourced? Yes,
so I'll answer this in this
Thanks,
is a technical one. So we have developed a full process envelope for PYROCO, and we have looked at moisture content, solids content and calorific value present in biosolids, because biosolids, depending on where you're harvesting from, which location of the plant you're harvesting from, its calorific value and solids content can be significantly different. So what we have looked at is that particularly with PYROCO, if you have 25% solids and a calorific value of minimum 12 megajoule per kilogram, then you can run PYROCO in energy neutral mode. So you won't need any thermal energy. However, it would always need some electrical energy to run pumps, fans, blowers, compressors, and those side of things, but no thermal energy required for drying. So it will generate sufficient energy for drying if you have 25% solids and about 12 megajoule per kilogram calorific value.
Okay. And what are the consequences of applying biosolids with relatively low carbon stability to land versus PYROCO biochar? How differently do the materials behave in the soil?
Arvind, I think this is more for your side.
So this is this is something we need to investigate. Southeast water is part of the soil CRC. I think Locas is on the call. I think we're trying to organize, come up with a project for soil CRC to answer some of these questions.
Perhaps, Aravind, maybe you could comment on, or Eamon even too, that, you know, biosolids, when that goes into agriculture, that still has further carbon emissions associated with it, and continues to emit as it breaks down in the soil, whereas the biochar product, that is an inert carbon, and so its emissions are no further once it's in the soil, yet it still carries the nitrogen, the phosphorus nutrients with it. Do you guys want to add to that in any way?
I was going to say we can absolutely say that there's certain quite fundamental differences. The carbon stability is the first one, so carbon emissions from biosolids will continue. That's well established. The structure of the biochar is ideal for hosting microorganisms in the soil and moisture retention in the soil. So that's another fairly substantial difference. And there may be some interesting data around slow release nutrient value and the reduction in leaching of nutrients when they're not being taken up by plants associated with biochar. So, but as Aravind was rightly said, those characteristics need to be quantified, but they certainly exist.
I have another question for Kalpit. One of the key issues considered in licensing biosolids biochar production in Queensland has been ensuring compliance with PFAS emissions limits. What emissions treatment is being used, planned, and what are the planned PFAS emission limits?
So for PFAS, the current regulatory guidelines suggest that for contaminants such as PFAS, you need to thermally destroy them at a temperature of at least 900 degrees for at least 2 seconds. If you provide this 2 seconds residence time above 850 to 900 degrees centigrade, then you should be able to get rid of PFAS. And PYROCO has demonstrated that successfully, that they were able to completely destroy PFAS. Also, Pyrage, their plant with Bioforce C-Tech in California, they also did the mass balance around PFAS, and they were able to see that if you provide 2 seconds and 900 degrees and above in a thermal oxidizer, you can destroy PFAS. Similar way, we also in our demonstration plant attempting 2 seconds and 900 degrees centigrade in a thermal oxidizer, but for pilot plant, we actually only had 0.6 seconds residence time and about 900 degrees in a combustor, and we were hardly able to get PFAS into our scrubber. We could not close the mass balance because the project was more focused on technology demonstration, rather really looking at the peripheral issues and all. But now we are geared up to do the proper PFAS balance. And the reason I'm saying why we might need a lesser residence time compared to others is our combustor, particularly around PYROCO, is highly turbulent. So we expect that kinetics will be improved with that increased turbulence, and that way we might need much lesser residence time compared to other technology providers for PFAS destruction.
So I have a question for David and Eamon. Which market will you target for the biochar upon operations commencing?
Maybe I'll start that one talking about Southeast Water, and then Eamon can pick it up in the broader market. So our initial intent is, well, we're currently distributing biosolids to agriculture, to farmers in our local area to improve their production and their pastures. Our intent will be that rather than distributing biosolids, we'll be distributing biochar to them instead. There's lots of potential that we've been identifying, and Eamon can expand on this, potentially into construction and roadways, but also into landscaping type of applications as well. And there's heaps more. Eamon could talk for probably another hour on this, but do you want to pick it up, Eamon?
Yeah, sure. Thanks, Dave. So the market for biochar is quite broad and relatively immature. We have a market established for biochar within road base, where we can sell biochar at a reasonable value within the road base. The biochar has been, certain biochars, should I say, it all depends on the nature of the biochar, but biochar land application trials have been very successful in different scenarios in Australia and overseas. So broadacre biochar application is a very viable future market, but it needs to mature. It needs some additional studies. I suppose it's the range of the use of biochar, whether it's as an absorbent, whether it's used for a replacement for activated carbon in land, in industrial applications, is really quite broad, and we've commissioned a study to look into that. Initially, the low-hanging fruit, my own thoughts will be biochar will be sold into road base and into the compost industry initially, I would imagine. But in the long term, I think the broadacre application is going to be an optimal value, optimal benefit solution. But that market needs to mature.
Thank you all for your questions today and for attending our event. Thanks to IOTA, Southeast Water, RMIT. We will be in touch with further information and links, and you can look up the IOTA website for more information as well. Thank you all, and enjoy the rest of your afternoon.